Good morning, folks. This is the presentation in Lab 4, which is also on week number 4. Today, we're going to continue with assembly analysis. And on the agenda, I have basically two chapters that I want to do. One of them is actually should be A, B, C, D. One of them is chapter 15, which is a shrink fit or press fit problem. Now, obviously, this is the same thing. And then I'm going to assume that these two things that are shrink fitted are actually thin discs, but we'll talk about that later. And then once I'm done with that, I'm going to do chapter 18, which is a bimetallic strip. So let's start with the shrink fit problem. Suppose we have two discs like that. Let's pretend that these are actually uh, not very long. So think about it as thin discs as far as the thickness is concerned. One of them is made out of brass, okay, or bronze actually, bronze, and the other one is made out of steel, okay. So the gray one is made out of steel and the yellow one is made out of bronze. Now, if you look at the dimensions here, you see that actually the outer diameter of the bronze is about 0.002 inches bigger than the inner diameter of the steel. In other words, if you wanted to take this bronze piece, the yellow piece, and stick it into that gray one, it won't go through, okay, without damaging it. So the way they put this thing in there is heating up, for example, the steel piece to make it a little bit bigger, and then put the bronze piece in it, and then let it cool down. This is called the pressure fit or press fit problem. And what happens because this bronze one is a little bit bigger than the steel one, obviously it's going to get compressed, and the steel, once it cools down, is going to get under tensile pressurized from inside. Now, the size of that pressure that develops at the interface of these is extremely important, because if it's too large, it actually makes the material to yield, and if it's too small, there's a possibility of these things become loose if, for example, the whole assembly is rotated, just hypothetically, okay? Now, there is a formula for the analytical formula for two discs, as you can see here, and it is it's the pressure at the interface. And notice what it depends to is, first of all, delta. Delta is half of this diametral interference. So 0.002 divided by 2 is going to be 0.001. That's the delta. A, B, and C are the nominal dimensions. For example, although it is true that B is half of this 4.002, but the nominal dimension of it is 4. Okay, so the material properties of steel and bronze pop up here. There is going to be your Young's modulus for the steel and the bronze, and Poisson ratio for the steel and bronze appear here. And what you want to do is solve this problem as an assembly problem. Okay. Now, before we do that, I want to show you, say a few words about the analytical solution of this thing. This, of course, is the pressure fit, interface pressure, and you should be able, given these dimensions, you should be able to stick it in there and work it out. That's a perfectly legitimate expectation if you know the material properties and these nominal dimensions and the radial interference. But when you look at it, the things that are as far as the stresses is concerned, the radial stress, so radially out, hoop stress, and the axial stress are of significance here. If the discs are assumed to be thin, then the axial stress is 0. So there's nothing stops it from shrinking or expanding. So the axial stress, for all practical purposes, is 0 if we're dealing with thin discs. And the hoop stress is the going around. The hoop stress, actually, you can plot it, and you can see it here. So if you look at this particular problem, for the information that's given, the hoop stress is this thing that actually is discontinuous at the interface. So this is the hoop stress in, or tangential stress in the bronze, and suddenly there is a jump because there is a abrupt change in material property, Young's modulus, and this is the hoop stress in the steel piece. Okay, the radial stress, on the other hand, which is this dotted line, is continuous, and needless to say that at the interface, it becomes that interface pressure, that pressure. Okay, all right. So what is the difference between having a thin disk and a very long cylinder shrink fitted inside of the other one? If we have a long cylinder shrink fitted inside of another one, then what you do is you take a cut. You take a cut. There's let me put it this way. If it's a long cylinder shrink fitted inside of the other one, there is no axial strain, but there is an axial stress. And if you're doing that kind of a problem, you take a slice, for example, unit thickness, and then you put the top faces and the bottom faces on surface slider. Okay? But if these are thin discs that you're shrink fitting inside of each other, you don't do that. Whatever the thickness is, you take, and you don't put the surface slider on the top or the bottom. So that is the difference between a thin disc and a thick disk. In this particular problem, let me see now. I'm going to do it with, assuming that this is a thin disk so that there is no stress in the vertical direction. Okay. Now, the other thing is that I want definitely, if you take a thin disk, obviously this is what we're dealing with, there is a plane of symmetry halfway through that you should use it. If you're asked to use all planes of symmetry, and I'm asking you to use a 30-degree sector, here, okay, 30-degree sector and half the height. The height, I'm assuming that in this particular problem, I'm assuming that the height is 1, although it's not specified here, but I am assuming that this height is 1. So when it comes to modeling, 1 inch, so when it comes to modeling, I use half an inch only. Okay, so let's go ahead and make this thing, and because I know exactly what I'm going to be doing, half the height and a 30-degree sector, I'm not going to make the whole model. I'll just make that particular portion of it. So let's start with the product file. Product file. Immediately save it. So we go to File, Save Management, Save As, Desktop, New Folder, Shrink Fit. Shrink Fit. So this product is going to go there. And then I'm going to make a rectangle and shaft it, okay, to get the brass piece and then to get the steel piece. So insert a new part in there. Let me do the steel first. Right click properties. This is steel outer ring, okay. That is the instance name, and we go down here. Steel outer. All right, so let's go make it. Double click on this. On that vertical plane, I will sketch. On that vertical plane, I will sketch a little rectangle. The height of this rectangle is 0.5 because we're taking half the height of the assembly, 0.5. Okay, and let me see now. The inside radius is 2. The outside radius is 2.5. So let's go put some dimensions there. These are in inches from here to here. This is 2. And the outside, so dimension from here to here is going to be 2.5. 2.5. And we say OK. So this is the steel ring, exit, and shafted by, let's make it 30 degrees. First of all, 30 degrees. 30 degrees. And I put the cursor there, right-click Z. There we are. So this is the steel piece. And I'm going to put material properties on it. So apply material, steel on that part, and we say OK. Good. Now we're going to make the brass piece, not brass, bronze piece. So we go all the way to the top, click on the floppy so that everything is saved, and then insert a new part, say no, and call this thing bronze, properties, bronze. And this is the inner piece. This is the instance name, right click copy, and there's the part name there. Paste. There we are. We say OK. Let's make it. Double click on this. On that same vertical plane, I will sketch. Now, if I'm not mistaken here, the radius, inside radius is 1, the outside radius. Now remember, the outside radius is the nominal one is 2. Although it's a little bit bigger, 2.001, but we don't gain much by changing from 2 to 2.001. So I'm going to use the nominal dimensions for making this. So let's go back here. Let's make a rectangle. Clean it up. Okay. So the height is 0.5, just like the steel piece. So that's 0.5. 0.5. And the distance from here to there, that was 1. And the distance from here to here is 2. Not 2.001, but 2. Okay, so notice that they actually touch exactly at the same location up there. So we exit, and once again we shaft it by 30 degrees, and along the z-axis. There we are. And let me change the color of that. So let me see now. Right-click, properties, graphics. Let me change the color of that to, let me see. Okay, I may have to do it from, close that. I may have to do this. Right-click, properties, graphics. Yeah, you go make it yellow just so that it looks like that. And then I apply material properties on it as being that of bronze. So click on it, bronze on that part, say OK, and there we are. Okay, so all the way to the top, all the way to the top, and save it, floppy. Remember, if this was a problem on the final or on the test, on the midterm, you have to give us bronze piece, the steel piece, the product, and the CAT analysis file that we're going to do later on. Okay, good. That's pretty much it. So we're going to go to generative structure analysis. CATIA sees two solid object. Immediately it measures it right there. You can see that. Since I know that the critical area is around this seam, I'm going to refine both meshes around that. So we know how to do this, right? So you go to local mesh size. It says you have 2 elements. Which one do you want to refine first? So let's do the steel first. Click on it. It says, okay, where? So let me hide that guy. And I want to define it right here. And the value that I want to put is 0.0. Let's see, 0.05. How does it look like as far as the size goes? Yeah, you can see that. It's smaller than that. Very good. Now we do the other one. So once again, local mesh property. This is the one that we want to refine. And where is it that we want to do it? It's over here, right? And I use the same number. Okay, so let me bring this thing in the front so that you can see what's going on right there. And if I mesh this thing, I'll see that I have a finer mesh there. By the way, if you change this rendering to wireframe, you can see that those two elements that I refined that is right there. You can see that. Okay, so let me put this thing back where it was. Right-click mesh visualization. You're familiar with this. And you can see that around the seam, the elements are finer. Okay, good. That's pretty much it. So let's deactivate this, deactivate that. Okay. Surface slider, planes of symmetry, surface slider. So this face and that face. This face and that face. Remember, I'm not using the local access system here just to make your life harder. When I did the rotating disc, I created an access system here and used it, etc. But I told you that surface slider will do the job. It's just that there I wanted to show you how actually that particular feature worked. That's why I did it the long way. And the bottom surface of that and the bodies are symmetry planes, right? Good. Now, what I need to do is I need to create a connection, analysis connection. To do that string fit thingy, I have to do an analysis connection between the face of the steel and the face of the bronze. So I click on that. I'm going to hide the bronze. For the first component, I select the face of the steel. For the second component, I select the face of the bronze right there. Let's bring this in the front so that you can see what you have done. Notice that I create a connection right there, that little white dot. And in fact, it's right here, right there. Okay. And let's see. Let me see for a second. This is a shrink fit. Where is that? Where is this thing? Let's look at the face connection property. Once you create your analysis connection, you go to face connection properties. Scroll here. This was contact. This is a pressure fit or shrink fit. Pressure fit, shrink fit, either one. Okay, and you click on it. It says, where's the support? The support is right there. You can see that. There's the support right there. And the radial interference is 0.001 inch. 0.001 inch, half of the diametral interference. And you say, okay, this will automatically take care of the contact. In other words, there is no need to go and create a contact between these two faces. That will take care of it. Let's go and save our analysis file. So file, save management. This is the analysis. Save as. In that same folder shrink fit, the analysis is going to go. We say okay. And if you go and check that folder that I created, shrink fit, there should be 4 files in it. The product, the outer, the bronze, which was the inner piece basically, and the steel, which was the outer piece, and an analysis file. Okay, so let's go ahead and run it and see what happens. I can't remember whether I used linear or parabolic, but I don't have a very fine mesh here, so either one it should have it should go through without any glitches. We'll see. It's doing it. See, the icon for pressure fit is something that looks like exactly what we did, something inside of something else. You see that here. Okay, done. So first, let's look at the deformation. There we are. Now, if you see what the heck is this, notice that the steel is going to be pushed out. The bronze is going to be pushed in by the steel, okay? And so in order for us to be able to see things on the screen, the CATIA program multiplies these by a factor. For example, 1,000 times make the displacement here bigger outward, 1,000 times displacement bigger here inward. And this is why you think that there is a gap there. To see the real stuff, first of all, I don't want to see these elements here. So let me double click on that. Selection. I don't want to see this pressure fitting connection stuff. All I want to do is the mesh for the outer ring and the mesh for the oops, not this one. Not this one. The mesh for the bronze inner ring. This is all I want to see. I don't want to see these other things there. And the scale for it should be 1. Scale should be 1 to see the real deformation. So I'll make this thing 1. And you see that they're actually touching each other. It should be. It should be. Let's look at the displacement. Double click. First of all, we make it average ISO. Okay, good. We don't want to see everything. We just want to see the first one and the second one. Good. And we want to set the scale equal to 1. And this is the real view. So material shading. There we are. Okay. Now you can see that the stress, you can see that, this is the displacement, right? So this is the displacement. Yep, good. Magnitude of the displacement. Very good. Now let's look at the von Mises stress. There we are. You can see that. So there's a stress variation, rapid change in color. By the way, if these smooth colors bother you, you just double click on it and then say more. Actually, that's not what I wanted to do. Cancel that. Double click on the legend here. Double click on the legend, the colors. And when this thing opens up, click on more. Not more. Back up. That's not. This is the dot that I wanted to move. Let me cancel that. Try it again. Double click on this. It doesn't bother me, but if you want to see clear cut changes in color boundaries, click on these 3 dots. See that? These 3 dots. Click on it. Say don't show me smooth. Uncheck it. Say okay, and say okay. Ooh. Oh yeah, you see that? The colors are not merging each other. You can see the clear variation here. And let's change the scale, the scale to 1 here. Good, good. Now, if you want to see the pressure at the interface, here's what we're going to do. I'm going to deactivate, which then you can, of course, compare with this number once you plug in all the information that you need for brass and not brass, bronze and steel. Okay, but let me deactivate this. I can see that this is slowing down for me. It won't happen to you at the university because the computers are a lot faster. This is a laptop, it's not doing very well. Deactivate this, and let me hide that for you. Let me hide that, and then we're going to say, okay, what I want is actually only the stuff on that surface. So that means you have to create a surface group. Here's the groups, and there is line group. This is surface group. It says, okay, where? On this, or on the bronze side. Okay, but I'll leave it like this. And then when you say, okay, show me back the one Mises stress, either double clicking on it or activating it, either one. He says, I don't want to see everything. I just want to see the surface group. Surface group right there. This is the one that I created. Just show me the surface group right there. Right there. And if you see that its color is weird, notice that on that face, I have a constant value for the pressure, essentially. So this is all numerical error. If you put the cursor on it, you see that the numbers are around 10,000, around 10,000. 10,000 psi. This is the von Mises stress at the interface is around 10,000, 10,400, 10,500, 10,600. The moral of the story is that this is all numerical noise, you can see. And this number, you can go, whatever this number is, roughly 10,000, 10,400, 500, you can go and compare it with this once you plug in the values. All right, folks, so that takes care of our first problem. Notice that in the lab, at least I think in the afternoon group, if I'm not mistaken, one or the other, I'm asking you to do a homework which is fairly similar to that, except that the geometry, the outer ring has some holes on it. So if you're doing that, then obviously this formula is not valid anymore. If you have a bunch of holes here, this formula is not valid. This is only for two uniform disks like that, okay? And then you have no choice but to do it with finite element. So let's go to our next problem, which is a bimetallic strip. This is the fundamentals. This is the fundamental idea behind the old thermostats, where two different dissimilar material metals were bonded together. And what happened is that when, for example, here aluminum and steel, aluminum has a higher coefficient of thermal expansion than steel. And these are fully bonded together somehow, and if the left end of these, the left faces of this are clamped, then when the temperature goes up, because aluminum wants to actually expand more, okay, and steel will not do it, this will either go up or down. And we can actually see what happens later on, and we come back to analyze it, okay? All right. Okay. Now, something else. You're asked to use as many planes of symmetry as possible. In this particular problem, notice that this is a plane of symmetry, so you can cut it in the middle and vertically down. There's only one plane of symmetry, so instead of going 1 inch, we go half an inch, okay? And we're going to do it like that. So the top is aluminum, is the bottom is steel, and we'll see how things go, okay? One other thing is that we raise the temperature. There's a uniform temperature rise of 50 degrees Fahrenheit. That means rise above the room temperature. Okay, whatever the room temperature is, above that temperature rise is 50 degrees. So if the room temperature, hypothetically, is, I don't know, 68 degrees, it's roughly room temperature, the temperature that you specify for this problem is going to be 68 plus 50. If you, well, just remember, this is a temperature rise above the room temperature. We'll come to that later on. Okay. Yep. So let's go out here. I'm not going to save any of this stuff. I'm going to cancel that. I'm going to cancel this. Start with the product file. And immediately insert a new part in there. And I'm going to call this thing right click properties, or call it top piece, aluminum or aluminium. I don't know exactly. One is going to be a typo in CATIA. The other one is okay. I'm not sure whether it's aluminium or aluminum. We'll find out. Okay, so this is a right click, copy, paste. Say okay. Let's go make it. Go here, double click on that vertical plane. I will sketch a rectangle which is 6 inches long and let me see now, just 1 second. 0.25 0.25 inches high, and then padded by 1/2 inch. Okay, so this is 6 inches, and this is 0.25. Okay, exit, padded by 0.5. So what you see here is half of this top piece. Now we have to apply aluminum properties on it. So you apply material here, aluminium. Yeah, be careful because this can cause you problem later on after the midterm when we do other things. Aluminium, not aluminum. Okay. So on that part, say okay. There we are. Now let me double click on this, show you something. If you click on the analysis, you see the coefficient of thermal expansion here. You see that? This coefficient of thermal expansion is what is needed, but this is at some reference temperature, and the reference temperature is the room temperature. And I'll show you what that thing is, okay? So this is, we can always change this, of course. We can go and change it to degrees Fahrenheit. So actually, let me do that. We have time. Let me do that. So we say, okay. Let me go to tools, options. Okay, under parameters and units, alphabetically order them. So coefficient of thermal expansion. Let's see if we can find it. This is alphabetical. Unfortunately, I cannot search this, so I have to you have to be patient. Thermal. Let's go to thermal expansion coefficient. Maybe thermal expansion. Let's see. Up. Ah, no, this is thermal conductivity. First of all, temperature. Let me change it to degrees Fahrenheit while we are at it. Okay. And then click on it. What? So far, we changed the degree. Let me see what the exact name of that thing was. It was thermal expansion. Thermal expansion. Okay, let's try it again. Tools, options, thermal expansion, right? It's hidden somewhere. Yeah, I don't see it here. So it really doesn't matter because it is the correct value, but it's in different units. It's gonna use it. I cannot find thermal expansion coefficient here. Uh, let's try it one more time. No, that's okay. Just leave it the way it is. Okay, fine. Now, uh, let me go and share. This is aluminum on the top, right? Yeah. So now we're going to go there, insert a new part, say no, and I'm going to change the name of this thing to be bottom steel, right click properties, it's the bottom steel, and bottom steel. Okay, good, let's go make it. Double click on that vertical plane. I will sketch a rectangle just like that, same dimensions. So let's see now, this was 0.25, right? This was 6. Very good. Exit. Oops. It was 6, right? Let's go back here and see what it is. 6. So that top one must have been wrong then. Is it? Oh, let's see. Maybe that's an illusion. Oh, yeah, that's an illusion. If you look at it like this, they line up. You see that right there. Okay, and then pad it by 0.5. Okay, let me change the color of this. Right-click properties. Properties. The steel, I'm going to change the color to something else, maybe yellow. Okay, good. Now, let's apply material properties to it, made out of steel. So, where's apply material? Right there. Steel on this part. We say OK. Good. Now remember, don't forget to save these things, etc. So now we're going to go to start, analysis and simulation, generative structure analysis. It's a static analysis we're doing. These are horrible elements as far as the size goes. Let me make this thing 0.1 because remember this whole thickness was this whole thickness was 0.25, and it's parabolic by the way. That's fine. And also this one is 0.1. Okay. Just so that this thing runs maybe faster, I'm going to double click. I'm not going to use parabolic. I'll use linear. Okay, very good. Now, what do we know? Let's change the rendering here. Change the rendering. Okay. So these two end faces are clamped. So click on this. This is clamped, and this is clamped. Okay. We took half of the, we took a cut here, right? We took a cut right there. So what we do is, we put the surface slider there. So surface slider there and there. Now, we know that these two pieces are fully bonded. Fully bonded means that they are, another way of saying it, welded together or fastened together. You know what? let me show you what happens if I actually did not make it fully bonded, but instead I made it sliding on each other. That's wrong. This is not what I want, but I want to show you that. Okay, first of all, create an analysis connection. First component, the order doesn't matter, top of this, top face of that. Second component, bottom of this, right? Yeah, bottom of that. This was the aluminum piece, right? Yeah, good. Let's bring this in the front. Okay, good. So I created an analysis connection here, and I'm going to make this thing contact. It is not contact because we said it's fully bonded. Fully bonded means that they're welded together, or think about it as fastened together. But let me show you what happens if you actually make it contact. You know how to make contact. Face-face connection, right there, contact. That's going to be contact. And never mind about these. We're not using these guys. We say okay. Okay. Now, where is the load coming from? If you look in this toolbar under loads, this one we have never used. It says temperature feed. You click on it. It says, okay, temperature, right? First of all, let me clear this so that you don't get confused. This is under a temperature rise. You see that there's a big T here? And this is under a temperature rise. But the question is what? Let me put 50 there for you, okay? Because this is supposed to be, this says temperature. It doesn't say temperature rise, okay? Let me put this thing as 50. This is wrong. You'll see why. You say 50 degrees Fahrenheit. Remember, I changed my unit to Fahrenheit, so this is correct. Now, notice that this thing was not there. It came up because we clicked on that temperature. Double click on it. It says the room initial temperature. That means the room temperature is actually 68. So if there is a temperature rise, the actual temperature will be 68 plus this. If you make this thing 0, then 50 would have been okay. But that thermal coefficient that we have in the database is associated with this room temperature. So we say, if that is the case, I'm going to go here to that temperature that I applied on the load, temperature field, and add to this 68. So it's going to be 118 degrees Fahrenheit. 118 degrees Fahrenheit, very close to it. So this is the actual temperature. Above the room temperature, that means we are dealing with a 50 degrees temperature rise. Now, if we run this thing, you will see something weird. That's because of that connection that I created. Okay. You will see when I say show me the deflection, you will see that this top piece, which is aluminum, slides longer in the axial direction than the bottom one. Right there. You can see that. Okay. That's because these are sliding on each other. But they're not. The whole purpose of a thermostat, a bimetallic strip, is that they're fully bonded. So let me go ahead and just delete that, deactivate this, deactivate that. Let me go ahead and that contact property I delete. Now, when you delete it, you cannot delete it from here. Notice that in the nodes and elements, there is no right-click delete. You have to go to properties, right-click delete. Make this thing a fasten. So look at the face-face connection property right there. Face-face, we have used contact, we have used pressure fit, right? The third one, it says fasten. Fasten. Fasten means that they're fully bonded, perfectly welded, fasten, they go move together. So you click on it and from the tree select that connection. Okay? And notice that the fastener sign appears here, right? And we're going to run it. And you see that it actually bends. That is the whole purpose of a mechanical thermostat. okay? And it goes actually down. So let me, what is this? One Mr. So let me actually show deflection for you right there. Change this thing to average ISO, and rendering, change it to material. Okay, right here. Let me also show you the element edges. Okay, good. Now, what happens is that if you look at the view from the front, you see that it actually bends down because aluminum wants to expand more. It's on top. And the steel says, no, you can't go where you want to go. So I'm going to, limit your movement. This bends down. So if the material, if this was a temperature drop, it'll go exactly the opposite side. And now if this was a temperature drop from the room temperature, this will actually bend up. Okay? So I want you to think about this. Just don't let it go over your head. And so one goes up, the other goes. Make sure you understand what the issue is. And if you look at the von Mises stress, now you have to be careful because there is a discontinuity across that interface. They're two different materials. So it's not surprising that you have a sharp, basically, difference in colors. So you really have to be careful to take these numbers for granted. You have to have a fine mesh above and below. Otherwise, this is just a good-looking color. Don't rely on the numbers. The behavior showed the overall behavior was okay, but don't rely on the numbers just by thinking about it. So as a matter of fact, let's see now. By the way, notice that uh, it looks like the biggest stress. I mean, if you trusted these, which I don't, is at the wall. Okay, let me go and do this thing with parabolic one, see how much it matters. This is 1.6. This is 19,000 psi basically. So let's make it parabolic. Let's make this thing parabolic. Let's run it and see how much that value is going to change. 19,000. I don't trust that necessarily that number, but I want to know. It's a good indication. Should I have trusted or not? So we go down here, right click, one misses, right click, activate. You see, 40,000. So it's so easy to generate these things without knowing how good they are. So one has to be very careful. I've already told you that this is a quick way of kind of discarding the results that you generated initially. You go from linear to parabolic, suddenly the thing doubles, okay? And from this point on, you really have to do mesh conversion study, and you can't just trust these numbers, all right? So that takes care of our second problem.